Hi, everyone. Thanks for joining me for this short video describing my poster, What Can We Learn from Lithium-Rich Giants in GALAH? I'm Sarah Martell from the University of New South Wales, and the work I'll be talking about was done in collaboration with Jeffrey Simpson, Aditya Balasubramanian, and the GALAH survey team. GALAH is a large spectroscopic survey that we've been running at the AAT since the end of 2013. And so far, we've observed over 700,000 stars. Most of those are analyzed and available in our latest data release, GALAH DR3. As a galactic archaeology survey, we focus on the stars that can tell us the most about the history of the Milky Way. We have a very thorough sample of the nearby disk, and for all of our stars, we derive important quantities like ages, kinematics, and the abundances of 29 key elements. The project that's the subject of my poster is looking at lithium-rich giant stars in GALAH. Lithium is an interesting element because it's produced in Big Bang nucleosynthesis, but almost every process after that destroys it. This includes stellar evolution, so stars begin their lifetimes with the same amount of lithium as in their local ISM, but it's destroyed as time goes on. This diagram from Lin 2009 shows the lithium abundances for stars in the globular cluster NGC 6397, and this is what we expect lithium abundance in stars to do over time. As stars evolve, they move to higher luminosities, lower surface gravities, and their lithium abundances drop smoothly. Around 1% of the time, though, evolved stars like red giants have high lithium abundances, sometimes even higher than the Big Bang nucleosynthesis level. There have been a number of different mechanisms proposed for how to produce that lithium, and a lot of literature with small observational data sets that evaluate which models make sense. But we really need a broad enough sample of lithium-rich giants if we're going to understand which mechanisms are actually responsible for this lithium production. What we've done in our project is to go looking for lithium-rich giants in GALAH to see what we can find. Here's the GALAH version of this diagram, and you can see that a small fraction of the stars have quite high lithium abundances. What we find is that there are 4 distinct kinds of lithium-rich giants, and we can see them all in this diagram. There are luminous red giants, which are expanding and may gain extra lithium by engulfing their gas giant planets, or they may produce it internally. Red giants at the luminosity function bump, which have just had fresh hydrogen mixed into their hydrogen-burning shells, and their internal structure is re-equilibrating. Red clump stars, which have already been through the giant branch phase. They've had a helium flash to ignite core helium burning and are re-equilibrating after that. They can also be affected by tidal torques from a binary companion. And the secondary red clump, which is for stars that are a little more massive and started their core helium burning without a big flash event to disturb the interior structure. We already know these stars are rare, and there's a lot of literature on possible trends between lithium richness and metallicity, evolutionary phase, binarity, and rotation. What we learned from the GALAH data is that the probability for a red clump star to be lithium rich is over twice the probability for a red giant branch star, which may mean that there are separate processes at work in the two groups. That the probability to be lithium-rich is higher for higher metallicity stars, with a smooth increase for red clump stars and a sudden jump at solar metallicity for red giant branch stars. This indicates that the internal structure of the stars, which is less compressed at high metallicity, may control how easy it is for lithium to be internally produced or transported to the surface. That rapid rotation is correlated with high lithium abundance in red clump stars specifically, which might support the idea of rotationally driven mixing, or it might be a sign of tidal interactions with a binary companion. So that was a pretty quick tour of what we did in the paper. If you want to see all the details, I'd be happy to talk to you about it, and you can read the whole thing in the monthly notices, volume 505, page 5430. If you want to get the GALAH DR3 dataset, with all the spectra and the catalogs of stellar parameters, abundances, ages, and kinematics, you can get those at galah-survey.org. And if you want to see regular updates from the team, you can follow us on Twitter. Thanks so much, everyone. I'll talk to you later.